Then you have the SPS ring, you have the LHC ring, and it's now a collaboration of 140 people, 28 institutes, 14 countries, and it has this very strange cross-section that people have different things in mind. As you see here at the top, QCD, neutrino beams, cosmic rays, and high PT physics. And everybody gets a chunk of time and everybody does what he wants to get from the experiment. But the detector is universal enough that he can serve everybody. And this is a list, and actually the neutrino people came in late. So that wasn't initially planned. So we had T2K people doing fantastic measurements. Then we have now, the latest incarnation is Dune, actually from the US, a group working on this, trying to measure the yields of pions and correspondingly of neutrinos for replica targets and other things. And the instrument works very well. And the cosmic ray group is actually very small. It's KIT, it's Hawaii, and here a group in Poland. And the others are really, but we of course use the same calibration, use everything. So the things work together, but the data sets are different. Now, why is NA61 such an interesting experiment? So we have the SPS beam. So think of 450 GeV or in this range, up to 550. And then you can put it on a target, like this beryllium target of 18 centimeters. You have all sorts of spallation products, and you can select by magnetic rigidity the target you like. Or you can tag then with Cherenkov's threshold detectors and others. And that means you can have all the beam from lead down to individual elements. Of course, you can also have pions. Here you can have kaons. You can have whatever you like as a primary. Of course, you can't have pions and kaons up to 500 GeV. That's not working. You have typically 350 is a sweet spot where you get lots of secondary particles you can use. And the instrument is very, first of all, this pre-selection here of the H2 beam line is actually very good. So you see it here with a momentum resolution of 2%. And it's rock solid. It's running there for many, many years now. And we know how to use it. And you just wish what you want to have and you get. Now, the instrument itself is really, it's from basically 1994. It has two big superconducting magnets that we inherited also from a previous experiment. At the time, NA49 inherited it, the big green magnet. And then as a vertex TPCs here, and as a main TPCs here, here's a target, and the beam is coming in here. And when we started, the beam was literally going 10 meters through the air before it hit the detector. Now we have a helium pipe there to reduce the interactions in air. And you have all sorts of beam monitors, scintillators here to select the proper thing. And you have, this is like the forward fragmentation detector. You have gap TPCs and all sorts of things. And you have, of course, your time of flight walls that are very important. This is just to give you a scale how big it really is in real life. Well, you know, it's all housed up, so you can't really photograph it properly. But here you have a person to give you a scale and size, what it means. This is if you photograph it inside. You see, this is what you don't see is a vertex TPC. Then you see here, this is a main TPC, and here the beam pipe. And this is how it looks like inside. Okay, and this is the early days. And you see the KIT people I selected here on the photographs. This is an upgrade program where we put out the old cables from NA49. There's a lot of copper that we actually could recycle. And this is one of the first data taking in 2009, where we really got our first data for cosmic rays. And it's really an experiment where you do the coincidence or anti-coincidence by plugging a cable and putting it somewhere else into the part so it's all manual. So it's really like a textbook experiment you could run as a advanced lab course. So it's beautiful. Unfortunately, not nowadays anymore because we have improved it. Okay, anyway, you see the superhero here, and this is Michael, because he has really made a full program out of this, what we started at the time. And this is one of the events that we have recorded. And so you see the main parts that we really need is the vertex TPCs where we have two magnets. There you see the bending power. And then you have the straight sections, that's the main TPC, and you have the time of flight walls, of course, and you have a gap TPC here, and you have, of course, the beam detectors here. And it's, again, a textbook experiment, how you identify particles. So with the bending, you get charge times momentum. With the energy deposit, you get essentially what the mass of the particle, so you can get the individual tracks like for the kaons, the pions, the antiprotons, and so forth. You can determine the mass of the particles, and actually with a very good resolution. And in principle, we don't exhaust at all the capability of this experiment because it was built for heavy ions, and we have just a few secondary tracks. So we have a comfortable range we work with. The only drawback is actually that this experiment takes data only at 100 Hertz. That's a very low rate, 100 Hertz. So that's a big problem because we can't read it out. And we fixed this in between. But when we took our data that I show here, it's all 100 Hertz data. And anyway, just to show you how this works for the different particles, you see here the labels, protons, kaons, pions, electrons, how you group them, and how you do the reconstruction for different momenta. Now, we have done quite a number of measurements since then, and it's two groups of data. One is for air showers, so it's proton-carbon and pion-carbon interactions. And you see 30, 60, 90, 120 GeV, pion interactions 30, 60, 150 or 158 to be more precise, and 350 GeV. And you see the secondary particles we have measured with a very large acceptance range. And here is the sigmas and the cascade and whatever, which are less important for us for the air shower simulations. And it's 13 papers that are listed below in gray, where you can look up the different tables. But of course, you can also go to the Durham database and download the tables directly. That's all published. I'm going to talk about two recent measurements that are of interest here. And so I'm not going to go through and just show you pages and pages of plots. Of course, here, quite a number of measurements. If you ask yourself, why have we measured 120 GeV? This is because the neutrino people wanted to have 120 GeV. Or why have we measured 31? This is, for example, T2K. So you have the different beam momenta that are important for neutrino experiments, for neutrino beam experiments. Okay, one of the important things is, of course, in the air shower, the energy is way too low. But if you look at this sub-cascades in the shower that evolve, you get all the re-interactions down to very low energy. And you know, we talk about the muon problem. And one of the things, how to enhance the number of muons is keeping, like if you have a pion, something else, you want to keep the this energy in the pionic channel that is not neutral pions. But of course, from time to time, a charged pion will convert in a leading pion that is a neutral one that will immediately decay. You could avoid that by not making a neutral pion out of it, by making it a Rho meson, because a Rho meson decays instantaneously into charged pions again. And that's something, for example, and Sergei is here, that has been put forward some years ago as one of the important effects that could enhance the muon yield of air showers. The other effect that actually goes back to Peter Grieder years back is having much more baryon and antibaryon pairs being produced, because baryon number conservation makes sure that the baryon is going to stay around for essentially all the time until annihilation. Annihilation happens basically at rest. And there are other things like Lorentz invariance violation. You can have lots of more kaons, like Luis Ancardogi has put forward, or other people before, but a recent paper published here, similar effects. And so it's interesting to measure this in NA61 because it's mattering when you come to low energy, when the cascade is going to stop or is going to continue, whether it's really there. And we knew from NA22, which is another experiment from CERN, a much earlier one, that for pions, pi plus on proton, we see a very strange effect. We see the neutral pions being produced this way as secondaries, and the Rho mesons produced this way. And the interesting part is the Monte Carlos, of course, typically treats spin particles like spin 1 and spin 0 like just a random flip between those with a adjustable number, how often you have spin 1 and how often spin 0. So the lines are parallel. And that's, of course, true for Pythia. It's true for whatever, all the models, if you don't do anything about it. But the data don't follow that. And some time ago in Sybil, and that goes back to 2015, basically, we worked on that and Felix changed it to reproduce the data, but we had to do it by hand because it's not implemented. And it makes a big difference because, of course, the neutral pions that we had dominating here would always go to the electromagnetic channel, whereas the rho mesons that dominate now at large Feynman X go into charged pions again. And if you try to measure this for carbon targets, this is proton target at 250 GeV. We have to see how big the effect is for carbon. So this is the run that actually we took just for this purpose. So it's 160 or 158 GeV and 350 GeV. You see here the secondaries just to illustrate this. And here you see the invariant mass fits. So you see very nicely the rho peak here for this data set and for the other data set. But you also see like kaons, you see omegas, F2s, you see the whole zoo of resonances you can think of. And that's only a section that I'm showing you here. The paper has lots of resonances. And so there are two papers published on this. One is just from last year, it's 2023. You see the top one. And the beam momenta, the secondary spectra of pions, kaons, proton, antiprotons, lambdas, K short, and then the rho, omega, and K star. And this is how it looks like. This is for the pions. Here in momentum plotted with the different models on top, QGS-jet, EPOS, two versions, Sybil. And these are models that existed before the analysis was finished. So that means we have not used those that could use the data. It's really a fair comparison for pi plus and pi minus here. And then this is probably what you are more interested in. This is a rho meson yield measured here at 158 GeV and a similar plot for 350 we have. And this is the antibaryons. You see, this is very hard to read. It's a P, a proton with minus, it's an antiproton that is an antiproton distribution. And you see that actually, although Sybil was already like 2.1 was without the effect, then the black line, we used NA22 as data reference, and we more or less got it right. Yeah, so it seems to be with the Glauber and additional energy losses, the effect is smaller, but it's in a reasonable ballpark. We didn't have the data, but it still looked fine. And you see, by the way, Sergei and QGS also worked on it and put by hand the very hard rho mesons in at the time. But I think, Sergei, you didn't care about the low part, right? Yeah. 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 And but for example, you see also a big problem with the old Sybil version for the antibaryons, which would have been a factor of too low. And if you now look what it means for air showers, it tells you not so much as we would like to, because the NA61 point is the one point we have here, for example, for the rho mesons, and for the baryons, we have the 2 points, and we have to extend those in energy to the highest energies because the process could be there all the way. And you see the different models do it different way. By the way, we see that EPOS has way too many antibaryons here, but not so many rho mesons in this version 1.99, that is the older version. This is really an open question still. Okay, this is then, you might ask, why did it take us so long to bring the papers out? And that's related to what we call the kaon puzzle. It's actually, the story is, a typical cross-check you do whether you understand all your resonances and short-lived particles, that you check K plus, K minus versus K naught short, and it doesn't work. So we do have an inconsistency in the data that we don't understand. It should be actually at 1. And because you multiply it by 1/2 here, and if you do the quark counting, it should be at 1, and it isn't. And we saw it the first time in the pi minus carbon data, and now we have taken lots of data with isobaric neutral, so that means same number of neutrons and protons in projectile target, where this should be exactly true. And we do see it's not. So there's actually a more fundamental problem that we want to follow up, and we don't understand where it comes from, but that's actually the reason why those papers came out so late, because we finally gave up and just said, we don't know. We don't understand it, we report it. And okay, the last part that I wanted to mention very briefly is a measurement on cosmic ray propagation, because this instrument is so powerful and universal, and you can have an arbitrary beam and target. So what we want to measure is how much boron is produced from carbon. So carbon is a primary element here. Boron, lithium, and beryllium are the secondaries that are missing in the solar population, but are available in the cosmic ray population. You know this. And there are lots of channels from carbon 12 to the different, like boron 11, 10, and all the way beryllium 7 down. And you have like oxygen contributing and all this. And that you can measure easily with NA61, because you do spallation beam, you identify your incoming ions, you just measure what's coming out. And so there was a pilot run, and well, no, I spent a minute why it's actually interesting, but it's probably here preaching really to the choir. It's, we have, for example, here the fluor and lithium anomaly that AMS has reported. And so it's really good to understand the cross sections. Otherwise, you don't know the ratio between the primary and secondary elements, or plotted here as secondary over primary. And so the cross section is a key also for the propagation column depths to calculate. And here, this is how the measurement works. You take a carbon, and then you have a target, and you choose different targets to subtract, because you want to have protons as a target in the end. And simply from the deflection, you know, the momentum and everything. And this is how you select the beam. So you get immediately lots of different beam particles, and you get lots of secondaries, and can do all the measurements more or less at once if you have enough statistics. For the pilot run, we didn't have enough statistics. This is 2018. Anyway, you get lots of secondary particles, and we work with two targets, carbon target, and this is polyethylene, and an empty one, of course. And with this, you can do the combinatorics. You can do it on carbon, you can do it on protons, and you can do it, of course, on nothing for the background. This is the cross sections that we derive. And it's only, I mean, statistics is negligible, because we just wanted to see whether it's working. And if you get later a full run of 1 week that we have planned for a longer time, we expect to shrink, for example, the exponent delta and the diffusion coefficient and the zero from this red uncertainty line in the galaxy we have right now to this tiny black circle here. And of course, you can also use this data if you want to learn more how to simulate fragmentation in air showers, because you can also do exercise like this. But this is all not so easy. Shows you the proposal was made in 2017. Then there was this pilot run very quickly, granted by CERN, and a preliminary release. And then COVID hit, and we were always delayed. Like we were canceled in 2022, we were canceled in 2023, and we are now promised to do it maybe this year in November. But we don't know. This is how it is. You have to compete with big experiments. And if you do a nice niche type of measurement, it's not really getting granted the time. That's basically all what I wanted to show. Yeah. And thanks a lot.
Thank you for the very nice talk. And obviously we have questions from the audience.
Or maybe not. Yeah.
Hi. So yeah, thanks for the talk. I was wondering regarding the proton carbon runs, the maximum energy right now that's been done is 120 GeV for the momentum, right?
No, 350. Well, oh, proton carbon. Yeah.
Yeah, proton carbon.
Yeah. Simply because we didn't ask for more.
But
Yeah.
would it be feasible to get
Yeah,
more?
of course.
Okay.
We could even.
Because then we have the direct proton beam from SPS. Does it? So
Oh, we could go higher. We could definitely go higher if we want to, but we didn't see a need right now. Yeah. I mean, it's always we have to ask, and you have to go through SPSC, the CERN committee, and they allocate beam time. And if you have a good scientific case, and you have to show the scientific case what you improve, we get beam time. Well, no, it's not mattering enough to say there's a gap and I want to fix data more. You have to show how much things improve, which is sometimes really hard for those types of measurements. Whereas if you, for example, have a neutrino source and you want to know what the beam is in T2K or something else for neutrino oscillations, it's much easier to make the case. Yeah.
Ralph, I have a question about slide 11.
Yeah.
No, sorry, 25, which is a
Yeah.
carbon beam
Yeah.
on something.
It's not stuck yet. Okay.
25. Yeah,
Yeah.
yeah. So what exactly is the target here?
We have initially, no, so the beam itself is produced at a beryllium target, like 200 meters away.
Okay.
And then you select with rigidity. So you select actually A over Z, constant A over Z. You select, and then you have time of flight. And you have a Cherenkov counter with Z square. So you see on this side is time of flight.
Yeah.
This is a charge. Yeah. But you pre-select magnetically with slits the beam. And this is why you get those on top of each other. Yeah. And because they have the same charge.
I see.
And so we could also select something else if we want to.
Yeah, yeah.
But this is on beryllium. It's a lead beam on beryllium.
Okay.
So we actually need heavy ion beam for that, which is not run very often at CERN. But if you, so this is, we have like
Okay.
a lot of gymnastics with
Yeah.
logistics to get the time. But this is how it works. And of course, then you get part of the beam just going through that you see also here. Yeah. And then you get new fragments.
Okay.
Yeah.
Yeah. Then I understand. Okay.
Yeah.
Thank you.
But by the way, yeah, just this is here. This is shown now for carbon, for polyethylene inside or carbon. I even don't know which one this plot is referring to, because you subtract the two, because polyethylene has 2 hydrogen atoms and 1 carbon, and the other one has only carbon, and you have to subtract. Yeah?
Okay.
Yeah.
Would you please come back to antiprotons with the robots?
Yeah, yeah. This one,
Yes.
the gray is
It-
our
it-
boss. Yeah.
It's a bit surprising because when you check the particle ID,
Mhm.
it becomes worse and worse when you move to higher energies. I don't actually see it. And one more
Well,
point,
somehow you see it's getting bigger, but not much.
not much.
But this detector is actually not really challenged by those measurements. Yeah.
And second thing, you don't have a plot for protons, similar one, because the arrow bars are much smaller.
Yeah.
You didn't show it. And this I never understood. How come that proton ID is easier than antiproton?
I don't know. I have to check. Yeah, I really don't know. Because the protons should be equally, but it's true, of course, one is going in the other, one direction and one in the other. And the positive one is heavily used in NA61, because that's the typical way how we calibrate the beam. And actually, we use the fixed beam energy and shoot it in the detector and use a deflection to calibrate the TPC. And therefore, so it's one-to-one calibrated, whereas for the antiprotons, we don't have that. So maybe that's related to it. Yeah.
Maybe that's the
Yeah.
reason. So if no further questions, we thank Ralph again.